You know how when you look at a photo, your brain just knows what's close and what's far away? It's effortless for us. But for a computer, a photo is just a flat grid of pixels. So how in the world could an AI learn to see in 3D using just one single 2D image? Well, today we're going to talk about a breakthrough model called Depth Anything that's figured out how to do exactly that.
All right, so let's get right into the core question here. The fancy term for this is monocular depth estimation. Monocular just means one eye, or, one camera lens. The big idea is to get an AI to look at a regular photo and create something called a depth map. And that's basically a grayscale picture where bright spots are things that are close to you and dark spots are things that are far away. Sounds simple, right? Well, this problem has been a real head-scratcher for researchers for a long, long time.
And wow, just look at the result. It's pretty stunning. On the left, that's just a normal photo, right? Flat, colorful, looks like something you'd snap on your phone. But on the right, that's how Depth Anything sees it. Look at that detail. The person right up front is almost pure white, and the stuff way in the back just fades to black. This isn't just some cool filter. No, this is the AI actually understanding the 3D layout of the scene. So, how did they pull this off? Well, the secret is all about a totally new way of thinking about data.
See, anytime you want to build a powerful AI, you need a ton of training data. And for seeing in 3D, that has always been the biggest roadblock.
I mean, think about it. If you want to teach an AI what's near and what's far, you have to give it pictures that already have the answers, what we call ground truth data. And getting that data is a nightmare. It means using expensive LiDAR sensors, crazy stereo camera rigs, or spending ages doing 3D reconstructions from video. The researchers themselves said it's costly, it's slow, sometimes it's basically impossible. There was just no way to get enough different kinds of data to train an AI that could look at any photo you throw at it.
And this is where things get really interesting. The researchers basically said, okay, we're doing this all wrong. And I love this quote from the paper. We, for the first time, pay attention to large-scale unlabeled data. They decided to completely flip the script. Forget struggling to make a couple million perfect, labeled 3D images. What if they could just use the billions of regular, unlabeled 2D photos that are already out there on the internet?
And that is exactly what they did. They pulled together a jaw-dropping 62 million normal, everyday photos. We're not talking about special 3D pictures here. Nope, just regular photos of, cats, cars, mountains, cities. Photos with absolutely zero depth information attached. The scale is just immense. But it creates a whole new problem, right? How on earth do you train a student with a textbook that has no answer key?
Okay, so this is where their training strategy gets really, really clever. They came up with this pipeline that they describe using a teacher-student analogy, which makes it super easy to understand.
So here's the game plan. Step 1. They took the best data they could find, about 1.5 million images that actually had good depth labels, and they used it to train a pretty decent teacher model. Okay, step 2. They took this teacher model and set it loose on that giant pile of 62 million unlabeled photos. For every single one, the teacher created its best guess of what the depth map should be. These guesses are what they call pseudo-labels. And then, for step 3, they created a brand new student model from scratch. And they trained that student on everything, the original high-quality stuff and the massive pile of pseudo-labeled images from the teacher.
But here's the twist in the story. The researchers are really honest in the paper and say, at first, this didn't work, like at all. Just adding all that guessed data didn't make the new model any better. The student was basically just becoming a good copycat. It was learning all the teacher's knowledge, sure, but it was also learning all its mistakes and bad habits. The new data wasn't making it smarter. It was a dead end.
So, to get past this roadblock, they had to get really creative. They realized they needed to add 2 secret ingredients to the training process. 2 key tricks that would force the student model to actually learn and become smarter, instead of just being a copycat.
And those 2 secret ingredients were, number 1, giving the AI much tougher training puzzles, and number 2, forcing it to develop a deeper understanding of what's actually in the scene. So let's break down what that really means.
All right, ingredient number 1 was basically a form of tough love for the AI. Whenever they gave the student model one of the unlabeled images to learn from, they would just mess it up aggressively. They'd distort the colors, blur out sections, and even do this wild thing called cut mix, where they'd literally cut a piece from one photo and just paste it on top of another. The whole point was to make it impossible for the student to just cheat and memorize the teacher's answer. It was forced to learn the real underlying rules of geometry and 3D space to solve the puzzle, no matter how weird the picture looked.
Now, the second ingredient was, I think, even more brilliant. They figured that to really understand depth, the AI also needs to understand what it's looking at. Is that a car, a tree, a person? So they brought in a guest lecturer, another superstar AI named Dino2, which is famous for understanding the meaning of things in images. They added a new rule for the student model. Okay, not only do you have to get the depth map right, but your internal thought process about what an object is has to match the expert's thought process. This forced the AI to learn really rich details, so it could tell the difference between the front of a car and the side of a car, which is crucial for getting depth right.
Okay, so they had the massive data set. They had their two secret ingredients. Did it actually work? Let's look at the proof, because the numbers don't lie. So check this out. This is what's called a zero-shot test, which is the ultimate test. It means they're testing the AI on data it has never seen during training. We're comparing depth anything against the previous champion, a model called MIDAS. Now, the number we're looking at is ABS-REL error. All you need to know is that this is an error score. So the lower the number, the better the model is, okay? So look at the KITTI dataset. That's a bunch of driving scenes. MIDAS gets an error of 0.127. Depth anything? 0.076. That is not a small improvement. That's a massive, nearly 40% drop in error. It's a huge leap forward.
And if the table didn't convince you, this bar chart makes it crystal clear. That tall bar on the left, that's the error rate for the old MIDAS model. And the bar next to it, the much shorter one, that's depth anything. I mean, you don't need to be a data scientist to see what's happening here. This is just a fundamental, undeniable jump in performance.
But numbers are one thing. What does this look like in practice? Okay, on the left, you've got the prediction from the older MIDAS model. And hey, it's not bad, but look closely. You can see some blurry spots, the edges aren't super clean. Now, look at the depth anything version on the right. See the difference? The outlines of everything are so much sharper. The surfaces are smoother. The difference between what's close and what's far is just way more clear and precise. The quality jump is something you can literally see with your own eyes.
But hang on, because this is where the story takes another fascinating turn. The researchers discovered that by trying to solve this one problem, teaching an AI to see in depth, they had accidentally built something much more powerful.
It turns out to because of all that tough love training and that guest lecture from the Dino-V2 expert, the model's core brain, its encoder, got so good at understanding images in general, not just for seeing depth, but for seeing anything. So they decided to test this crazy idea. They took that core brain, the encoder that was only ever trained to see depth, and they tried it on a totally different task called semantic segmentation. That's where the AI has to label every single pixel in a photo, like this is road, this is sky, this is a person. And on the main test for this, the ADE20K benchmark, it didn't just do okay, it shattered the old record. It set a new state-of-the-art score of 59.4. This was a huge surprise. Nobody expected this. And the researchers said it best themselves. They wrote that it has great potential to serve as a generic multitasking encoder for both middle-level and high-level visual perception systems. In other words, this thing they built isn't just a depth tool. It's a new foundational building block for all kinds of future AI vision systems, from robots to advanced photo editors.
And this last set of numbers really drives that point home. This shows what happens when you use these different AI brains as the starting point for other jobs. Now be careful, for these numbers, higher is better, the opposite of the error scores from before. And look what happens. Whether you're doing depth estimation or that pixel labeling task, if you start with the depth anything encoder, you get a much higher score. You can see it right there. This proves it. You can build better, smarter, more capable AI by starting with this new foundation. So depth anything is a massive step forward. And not just because it's great at seeing in 3D. The real breakthrough is that it shows us a new way to use the gigantic piles of unlabeled data we have all around us. It's basically given AI a powerful, robust sense of sight. And that just leaves you wondering, right? If AI has now mastered seeing, what human sense will it conquer next?